Hello again, everybody, and thanks for checking back in. We've been talking about angular momentum and the fact that that is linear momentum times a radius, right? So angular momentum, oops, I didn't mean to do that. Let's do this right here. I'm going to fix something real quick. There we go. So angular momentum equals radius, which is a vector, times linear momentum, all right? But we're going to tie this in with torque, with Newton's second law. And we've done problems already where we, like Atwood machine problems, for example, where we use Newton's second law instead of summing up forces, or net forces, we summed up net torque to solve for an unknown force or an other unknown quantity. All right. So we're going to relate angular momentum to. We're basically going to arrive at this right here: how change in angular momentum over time, change of time, equals net torque, which of course we also know to equal moment of inertia times angular acceleration. Okay? Well, let's just state some of the things that we know right here. We know that net torque equals moment of inertia, right, times the angular acceleration. Right, that net torque is a vector, so is angular acceleration. And that's because, well, it's because we know that acceleration is a change in velocity over time. Well, angular acceleration is going to be a change. I'll write my I again right here. Angular acceleration is going to be a change in angular velocity over time. All right, in some amount of time right there. All right. Well, another way we can state momentum, aside from being, or angular momentum, aside from being radius times linear momentum, we can also write it as angular momentum is moment of inertia times, I should say times our angular speed, omega, right? Which means that a change in momentum equals our moment of inertia times our change in angular speed, omega, right there as well. Okay? So what we can do is we can take this, I times omega, and put that over t. This is really this right here. I'm trying to change colors. That is that, and we have a relationship now between angular momentum and torque. I actually have a lot more space here than I really need. But so we can say that torque, net torque, equals moment of inertia times angular velocity, which equals this right here, this change in momentum, change in angular momentum over time. And that's what we have at the bottom right there. All right, so it's the relationships between all these different values. It's actually the same relationships between the values that we learned in previous chapters, but this is all just in terms of rotational values. Instead of force, we have torque. Instead of mass, we have moment of inertia. Instead of acceleration, we have angular acceleration, and so forth. All right, what this means then is that if there is no net torque over time, all right, that means there's going to be no change in the momentum over a certain amount of time, which means that if net torque equals zero, then that means the final momentum and the initial momentum before and after a certain amount of time are going to be the same. A great example of this, and we may even have demonstrated this in class already, is over a certain period of time, if your mass changes, but there is, or maybe I should say your distribution of mass changes, but there's no change in torque, no external net torque from the outside, your momentum is going to stay the same. But if your mass changes, it means your velocity has to change. A great example of this is going to be figure skaters, all right? I'll show you that in just a second. Divers, hurricanes, and tornadoes, all right? If you look at a hurricane or a tornado well, hurricanes appear to move or rotate more slowly than tornadoes. Different parts of the hurricane, different parts of the tornado move differently. They move at different velocities depending on how far you are from the center of rotation right there. Pulsars, what a pulsar is a star that rotates very, very rapidly. So here's a diver right here, all right? And in order to rotate more quickly, to have a greater rotation, they appear to be rotating around counterclockwise. What do? They go into a tuck. They change their, this isn't really a term that we've used, but they change their moment of inertia. They can actually go from having their mass being spread out to being tightly compacted into a ball, and when that changes, when that takes place, you have a corresponding change in angular velocity. Why? Because the initial momentum and the final momentum are going to be the same thing. All right, we said, let me back up just a second right here. We said a minute ago that our momentum is moment of inertia times change in angular velocity. All right. Well, if there's no net torque, that means the final momentum, angular momentum, and the initial angular momentum have to be the same. Like I said before, hurricanes and tornadoes. Even though this is a still picture right here, it actually looks like this is moving a lot faster than this stuff kind of very gently moving on the outside. Now, to be sure, hurricanes aren't exactly gentle, but on the outer rims of hurricanes, I think they're moving slower. As you get more towards the center, they spiral and have a greater angular velocity than they do on the outside. All right. What else? Well, tornadoes. All right. This stuff here on the outside of the tornado is moving or rotating reasonably slow. Here on the inside, all right, it's moving very, very fast. So as your mass gets closer to the center of rotation, your angular velocity has to speed up. Why? Because angular momentum is conserved. All right. Out here you've got some angular momentum. Here you've got angular momentum. It's going It's going to be the same. This is a pulsar right here. It's a star that's rotating very, very rapidly. What they tend to do is they shoot out these. This is your axis of rotation right here. Actually, let me draw that in a different color. I'll draw that in, I don't know, orange or something like that. That's the axis of rotation right there. The reason we know that is because you can see that it's kind of shooting out these jets of material. But this whole thing right here, this is the disk. You might say it's the plane of rotation that all the other material is being whipped around it. All right, and as you get closer to the center, it moves faster and faster and faster. Why? Because momentum is conserved. So these are all examples of objects, people, meteorological events that conserve, or I should say that behave on the principle of conservation of momentum. You change your mass, and it's going to correspondingly change your velocity. So that is what the segment is right here. Angular momentum is conserved. Energy isn't always conserved, but angular momentum is, and we can assume that as long as the net torque, very much like the net force, coming from the outside, is equal to 0. All right? So that's it for this segment. Thank you for following along. Make sure you ask me if you have any questions, and I'll see you on the next one.